of the, or first pass of the motor prototype board schematic, ready to go into layout. So this is mostly just a review of the schematic. There's some stuff to do with power and interfacing to the development board that we're going to use to drive this thing, and that's about it. So let's get into that anyway, looking at the schematic in KiCad. Okay, so here's our schematic in KiCad. It's divided into 4 sections. The motor driver, which is up here, motor encoder here, power, and Nucleo connections. Nucleo is the name of the development board, the STM32 development board that I'm using to drive this thing. So much of this you've seen before. Let's take a quick look at the motor driver first. We have the Toshiba motor driver that I'm using here. The outputs that go to the motor. There's actually an interesting little KiCad thing here that I hadn't really known about before, which is that if you take a look at the motor, you see the reference designator has a hash at the beginning of it. Same with this connector, and what that tells KiCad is that these components are off-board components. They're not things that should appear in the layout. They don't appear in the BOM. They don't appear in the net list. But it does mean that you can show that there's a motor here. So this connector, this 2-pin connector, is what will appear on the board, and it's what we'll connect the motor to. The motor comes with some cables and some little pin header connectors, and we'll just plug those into a socket on the board. All the components around the motor driver, so there's power bypassing here, the stuff, the current sensing here, and the current regulation setting here we looked at in the first video looking at this schematic. The control inputs will come from the microcontroller, and we'll PWM one of those to control the motor speed. And I did some calculations based on the clock tree and in the processor on this development board and the oscillator that's available on the development board, and it looks like it should be easy enough to set things up so that we can do PWM at a frequency of 31.25 kilohertz. So that's the motor driver. We've also got this current sensing section here, because I want to do some experiments looking at the relationship between the current in the motor coils and the torque that the motor produces, and so that's easiest to do with by sensing the current through this current sensing resistor that the motor driver uses here. And so we've got an op amp to turn that into a decent range for the microcontroller ADC inputs. Then we've got the motor encoder stuff. We looked at this very recently, so I'm not going to say anything about it, except to say that I've tried to be fairly conservative in the design here, and we can basically test this part of the circuit completely independently via this test point here. We'll just wire up the power supply, put the photoencoder and these resistors on the board, and then we can check to see what kind of light and dark currents we get from this thing, just by interposing something in here to get the real dark current. That's the official tiny 100 nanoamp dark current that this thing produces, plus whatever extra you get due to ambient radiation in the wavelength band that the phototransistor is sensitive to. And the output from the comparator will go to the microcontroller board, and we will be able to use that to count pulses from the motor encoder as the encoder disk spins. So those are basically the functional parts of the board. We need to power the thing, and things like the op amps, the op amp and the comparator. So the op amp for the current motor coil current sensing, and the comparator for the photoencoder stuff will power from a 3.3 volt supply, and the same goes for the photo interrupter. And the Nucleo board provides a 3.3 volt supply, and so we'll just use that. I believe that the total current draw from these things and the photo interrupter will be less than about 30 milliamps. And the 3.3 volt supply from the Nucleo board is fine for that. The 4.5 volts for the motor, we could theoretically use the 5 volt supply that comes from the Nucleo board and just run it through a linear regulator to get 4.5 volts. But the current that the motor needs can be up to 250 milliamps. So at 4.5 volts, that's a 1 and a bit watts. And the way this is going to work is that the Nucleo board will be plugged into a PC via a USB port, and the Nucleo board only allows 300 milliamps to be drawn through the USB port. So you only have 1.5 watts in total there, and so running a 250 milliamp 4.5 volt motor off of that 5 volt supply coming from the Nucleo board might be a bit much. So what I'm going to do instead is I'm going to use a separate 5 volt supply, just a 5 volt wall wart, plug it into a barrel jack, and then use a linear regulator to produce the 4.5 volts. And the linear regulator is this TI part, the TLB702, and it actually comes in a 4.5 volt version in a SOT23, so that's quite nice. And the connection for it is very simple, bypassing caps. Just make sure the enable is enabled, so you get your 4.5 volts. So that's the power, and the wall wart can do 2.5 amps, so that'll be plenty. The only other thing is connecting this thing to the Nucleo board, and so these labels here, like input and output, are from the perspective of the Nucleo. An input is an input into the microcontroller, and output is an output from the microcontroller. And so we've got 2 power connections, 3.3 volts and ground, and 4 signals. First of all, we have the photo encoder pulse, which goes to the microcontroller, and we'll want to be able to count those, so we'll want to run an interrupt off the pin that's connected to, possibly also a timer capture to measure the intervals between the pulses precisely. For the moment, I've just connected it to this GPIO, which is on pin PG3 on the microcontroller. These labels down here are the labels of the pins on the Nucleo board. So the pins on the Nucleo board are split into a number of different connectors, like CN8, CN9, CN7, and so on. And then these numbers here are the pin numbers on those connectors. So this is a general GPIO input to the microcontroller. Then we have the motor coil sense voltage, and this needs to go to an ADC on the microcontroller, so that's an analog input. And the STM32 processor on this development board has lots of ADCs, and this pin connects to one channel of 3 of them, so that's easy enough to use. Then we have the 2 motor control outputs from the microcontroller, and they need to be PWM capable. So I've attached them to pins that are connected to 2 channels of one of the basic timers on the microcontroller, and both of those you can run a PWM signal from, or you can use them as a GPIO, because for the way the motor driver works, we need to just switch one pin on and off, and the other one will do the PWM on. And that's basically it. That's the schematic for this prototype motorboard pretty much done, and that means that we can move right on to layout. The first thing to do with that is to do some careful measurements of where the mounting holes for this PCB will be on the robot chassis, and to get the alignment and position of the photo interrupter just right, because that's going to be fairly critical. So I'm going to do that. Right, I've started doing some layout already, but I'll get onto that next, and in the next episode I'll just show you the layout. But probably show something to do with importing the mechanical drawings into KiCad for getting things precisely lined up. So that will be next time. See you then.